Good morning, everyone. We'll just give it another minute or two. We'll give it another minute or two for a few more attendees to join us, and then we shall begin the session. So this is our first session in breakout room number 2. I hope you've enjoyed the rest of the sessions across all of the breakout rooms. I am Antonia Albuquerque, and I will be hosting a few of the sessions in this segment. We have our first speaker, Anantharam Vanchiprakash. Anantharam has been working on distributed systems for the past few years and is extremely passionate about technology. He is going to be talking to us about how less is more, learning from optimizing and storing data. In this session, Anantharam will explain Flipkart's learnings while revamping the ratings and reviews system, which led to ad reduction of over 96% and a per host throughput increase of over 5x. Over to you, Anantharam.
Hey, thanks, Tony, for that introduction. Okay, so we'll get started. So before we go into the actual problem statement that we kind of solved, a quick display of hands is, am I audible to everyone over here? People can just put on the chat room, yes, no. Okay, awesome. This is good. So before we get started with the actual problem statement, let me give some background on the problem statement as a whole. So ratings and reviews is something that everybody who ever buys anything online would probably use to make a good buying decision, an informed buying decision. So as we would use a rating and review to identify what customers feel about the actual product and to understand what the product really is about. Now, in Flipkart, ratings and reviews are extremely popular, and it helps customers to make a lot of buying decisions. And if you look at the rating and review system as a whole, the rating and reviews is composed of a lot of functionalities. The first one is called a rating summary, which is what you see on the top, which is like a 4.1 star, 4.6 star. And then we also have ratings for specific aspects. Like if you look at a mobile phone, there will be ratings for camera, battery, display, value for money, and so on. There might also be images that would be there, which is around what are all the different images that a customer would have onboarded based on the product they've bought. And then comes the actual review as a whole. A review again has some title and some text and some images, along with upwards and downwards and things around it. Now, ratings and reviews, everybody knows, is extremely popular. Now, let's look at some stats of storing the ratings and reviews data. Right. The overall Flipkart has hundreds of millions of products, and we have more than billions of ratings. And this overall ratings in Flipkart is about 4.2 TB in size. And when I'm talking about 4.2 TB in size, I'm not talking about the images and the videos, obviously. I'm only talking about the textual data that is going to be there, and the index data that is required to serve the data. Now, the ratings and review is very important in the buying journey of the user. So the serving system, which is going to serve the ratings and reviews, needs to be an extremely low latency and high throughput system, because it will be shown across the entire buying funnel as the customer comes to search for the product, looks at the details of the product, and everywhere the ratings and reviews is required. So it's a very, very low latency and high throughput system. Now, to give you an idea about how much latency and how much throughput are we talking about, during a sale event, we typically see about 500,000 QPS on this system. Now, 500,000 QPS of serving 500,000 QPS of traffic just on the textual content is about 1.5 Gbps of traffic just on this system. And this is not including the images and videos. And you need to look at the B, which is a capital B and not a small b. So it's 1.5 Gbps of traffic. And to serve this kind of data at this high throughput, at that slow latency, we obviously need to store it in caching stores and in memory. We cannot afford to do a disk seek. Right? Now, we have about 100 instances of caching machines. We've used a combination of Redis and Aerospike, the usual suspects, for caching this data in memory, and we have about 100 instances of them. Now, This was all fine. We had 4.2 TB of data, but then went into an interesting challenge. The challenge was ratings and reviews is mostly available in English. When we wanted people in Flipkart to shop on multiple languages. As you know, Flipkart is already available in 12 languages right now, and we want to scale it up to 18 Indian languages. Now, for a customer who is talking Tamil or Telugu or Marathi, they might not have Marathi reviews and Tamil reviews automatically written by people who are shopping in the same way. So what we wanted to do was we wanted to machine translate all the reviews in every language and make it available in every other language. So the overall reviews for every language would be machine translated, and a new copy of those reviews, the translated reviews, would be available for customers to buy. So if you assume about 18 languages, and you assume that as more products get added to Flipkart and as more customers buy, the number of reviews also will increase in the platform. So if you assume 18 languages and 10x the number of reviews overall as a growth, we're talking about 180x of this data. Now, 4.2 TB, a back of the envelope math to store 180x of information would come up to about 700 TB to 800 TB of data. And as you know, the 700 TB and 800 TB of data needs to be stored in caching data stores in memory. And to store it in the caching data stores, we would need about 1,000 to 15,000 caching nodes at the same scale. Right. Now, this is obviously not maintainable and scalable. So we had to think about a new way of solving the problem. Now, different strategies are there. Vertical scaling, we all know that, but vertical scaling is obviously not going to work. We're not going to build a caching store which is going to have 700 TB of data. Now, horizontal scaling is the usual strategy that people use. Now, the reason why that will not work is you can keep on adding more shards. But as you add more shards to scale to 15,000 machines which are caching, it is just going to be extremely high maintenance. The probability of a shard going down at any point in time is always going to be a continuous factor because you have so many shards available. And if you're going to have more data per shard, let's say you're going to create big machines of, let's say, 1 TB of memory, which is not very idealistic, but let's assume 500 GB of memory, the recovery times when a shard goes down is also going to increase a lot. We face this problem even with 128 GB memory of Redis, that the recovery times actually increase a lot whenever a shard goes down. So we said this is not going to work and the usual strategies are not going to work. One strategy that could work is to reduce the overall data footprint. Now, in reducing the data footprint, what we mean is we store the same number of reviews. We don't kind of cut down on the number of reviews we want to store, but the footprint that is taken to store these reviews, we try to find strategies to reduce it. And that's the data footprint reduction model that we're thinking about. Now, when we think about data footprint reduction, what are the different strategies can we do? And the remaining part of the talk will primarily talk about the different strategies that can be used for reducing the overall data footprint. Now, the first strategy that you can think about is data cleanup. Now, what does data cleanup mean? When a developer writes an interface for a read and write, they would be having a very purist, uniform interface. It would look like read, read of an ID, and then it returns back an object, and then it will be like a write of an object which will write the object. Right? That is how you will write a purist interface. But for systems like these, where the writes might be happening on a completely different data store because it wants to be kept durably, and the reads are going to be happening from completely different data store because they have to be served at that scale, having a same data stored across read and writes might not be the best idea. There might be fields which are relevant for writes, but might not be relevant for reads. A good example for that would be a write might have a created at and an updated at. But when you're serving a read, you might want only one date to be shown. You would choose either created at or updated at, and you will only show that read. So having two fields of date might not be useful. We also had similar cases where, along with the customer name, we also storing the customer ID, where customer ID is never served as a part of the read request. We only want the name to be stored. So in the read data or in the data that is cached, storing the customer ID was actually irrelevant because it was never being read at all or never being used even if it was being read. So we had to get out of this purist interface model and try to make it in such a way that we only store the relevant fields that are required to serve the reads and not just have the entire object dumped in while we are trying to store the cached data. Now, this requires a refactor of the code, obviously, and by reducing the number of unused fields, we were able to reduce the data by about 10%. Now, 10% is not a big number, obviously, but it is definitely big when you have to scale to 700 TB of data. It does matter. But this is just one strategy that we used. We will go into another strategy. So as we all know, we have to serialize the data and keep. So we used to serialize the data using JSON. So a typical review that looks something like this would be serialized into a JSON with all the different fields like rating, title, text, and author, and it will have the values. Now, as you can see, the uh, orange color text over here is the schema, or it's the field names that we have. And this overall data is 150 bytes, out of which the schema alone is 60 bytes and the data is merely 90 bytes. So if I'm going to think about a billion reviews that is being stored, the schema is going to be replicated for each and every review, where it's actually going to be constant for almost most of the cases, right? So we said, let's use binary formats such as Avro, Protobuf, and Thrift. And for people who don't know about Avro, Protobuf, and Thrift, they primarily index on the fact that they try to keep the schema. These encoding formats are like JSON, but they try to keep the schema separate from the data. So if you have a billion reviews, the schema is actually kept separated, and only the data as is kind of stored. Now, just from this itself, if you keep the schema separate and you only create the review data for every review that you're creating, the overall data size will reduce by 40%, right? And it's also faster to process. Now, the overall output of this encoding will not look like JSON, obviously. It will look a little difficult to read because the rating key will not be there. It will be replaced by some kind of a number, and the number 5 will be stored in a different way and all of that. So it's not really human readable. But if you think about it, if you're going to serve billions of reviews and at the scale of half a million QPS, and you're trying to store that data, we should optimize on which would take lesser space rather than which is more human readable, because nobody is going to go and read a data from a data store when we are talking about this scale, right? Now, the question might be, okay, this is all great, but what if I want to add a new field? JSON just lets me add a new field. I can just look at it. Now, all these binary formats that I've talked about, like Avro, Protobuf, and Thrift, etc., they have extremely rich schema evolution. I put a link to how a schema evolution works towards the end of the slides. You can go read it up. But they have rich schema evolution wherein you can be confident that even when the schema changes, backward compatible, backward incompatible, all of that is taken care of. And they also support extremely complex data types, such as, you can have decimals and floats, which is really not available with JSON directly. You can even have objects as a data type added to it, wherein you can have a composition of objects and things around that, right? So it's extremely convenient and extremely useful to play around with. And that around just moving to Avro, Proto, etc., would reduce the overall data size by 40%. Now, of course, we could have just done that and we could have got a benefit of 40%, but we wanted to go even further than that, right? So some of the additional things apart from just moving to Avro and Proto was, given that we have now rich data types that is supported. ENUMs is a first-class entity that is supported by these encoding formats. Can we exploit ENUMs? So we said we will try to use ENUMs more than strings. Now, ENUMs are usually used by developers for, let's say, storing the day of the week, or the month of the year and stuff like that. But we wanted to use it for something more. So if you look at a review, the review also has the location from which the user typed the review, and the location has the state name. Now, the state name is typically stored as a string in the JSON. Now, what we wanted to do is we wanted to convert it into an enum. So every state now has an ordinal. So I don't store Andaman and Nicobar. I just stored the number 1. And because it's an enum, I can always look up by the ordinal and immediately get the data. Now, if you look at it, even the smallest state, Goa, takes 3 bytes to store as a string. But if you're going to store it as an ordinal, it will take only 1 byte. Now, for people who are thinking an integer is actually 4 bytes, but you're talking about only 1 byte to store, we will come to that in a bit. But as you can see, you will actually save a lot of space by just converting these strings into enums, which will internally get stored as integers. Right? Now, the next question that people might ask is, okay, this is great, but what if there is a state that is added newly? Or what if there's a state that is renamed and an old state is getting replaced and stuff like that, right? Now, as I told you earlier, Avro, Proto, any of these binary formats have extremely rich schema versioning. So you can actually have data which is a part of the data which is done with an old schema, a part of the data which is done with a new schema, convert an older data into a newer schema. All of their capabilities are provided off the shelf. So you don't need to really bother about having those kind of support for schema versioning, right? So given this this itself reduced the data size by a good number. Now, the second strategy that we used was we tried to use integers and longs wherever possible. And we'll come to where all we have used integers. But why is storing an integer more easier, right? So there is a concept called variable length encoding. Now, for the people who don't know about variable length encoding, I will just spend a minute to explain what it is. So let's assume that you want to store the number 1, right? Now, integer is 4 bytes. So the way in which number 1 will be represented would be 0, 0, 0, 0, 1 byte of zeros, which is 8 zeros, another byte of zeros, which is 8 zeros, another byte of zeros, which is 8 zeros, and then the last byte having 7 zeros and then a 1. So it's like, that's how the number 1 is being stored. If you look at the first 3 bytes have only zeros, and that will be the case for every number between 0 to 127. Now, technically speaking, for any number between 0 to 127, you need only 1 byte that you need to store, right? So what variable length encoding does is it kind of flips the bytes. So the last byte actually comes as the first byte. So it will just store 0, 0, 0, 0 for 0 and 1 and 2 and things like this. Now, for the number 128, the representation is actually all zeros, and then it's 1, 1, and then all zeros, right? Now, because we flipped it, the first bit of the last byte becomes 1. Right? The first bit of the last bit in a usual representation becomes 1. Now, because we've inverted the bytes, the first bit is actually 1, which gives the system a cue that it needs to read one more byte, right? And this byte actually has the preceding as 0, which means that it doesn't need to read any more bytes. So to store the number 128, we will need to have 2 bytes that we need to store, which is actually the most optimal way in which we can store 128. In this way, if you have smaller numbers, like for example, we'll come back to the older ordinals. Ordinals are integers. And because as long as you have only 128 states or less than 128 states in India, you will never need more than a single byte to store the ordinal. So these only use the required number of bytes to store a particular number. Now, the next question that somebody might ask is, what about negative numbers? Because negative numbers always start with a 1, right? So they all have ones all over the place. So negative numbers, even for -1, will take 4 bytes of data. Right? Which is where the second type of encoding comes into play, which is called zigzag encoding. Now, this is a very interesting technique. What they do is every number is mapped to another positive number. So 0 is mapped to 0, -1 is mapped to 1, 1 is mapped to 2, -2 is mapped to 3, and stuff like that. So what actually happens is, even for storing the number -1, I actually store the number 1. For storing the number 1, I store the number 2. I know it's a little confusing over here, but the reality is these two techniques actually reduce the overall data size by a tremendous amount because they optimally store integers. Now, you might be thinking, is this too much of code that I need to write and I need to bother about all of this so much? And what if I make a bug in all this? But the reality is you don't do anything for this. These are out of the box available. Move to any of the encoding formats. If you can take Avro, Proto, Thrift, to any of them, they all support variable length encoding and zigzag encoding out of the box. So if you just store them as integers, these formats automatically encode them in the best way possible and store it and save your space. So you really no need to bother about writing any of this yourself. Now, as we know, they are obviously much smaller than strings. And it's also true that they can be compressed. If you have an array of integers, they can be compressed much better than an array of strings. And we'll come to that in a little bit. Right? Now comes the next part that we need to remember is it is not always integers that we can store. We might also need to store decimal values, right? Floats or doubles, right? Now, one of the things that we always need to remember is whenever you're storing a decimal value, always attach a precision to it. Now, for example, the rating summary 4.1 star, 4.5 star is actually a decimal value. Now, if I'm going to store it as a mere float object, it will have a precision of 8 numbers. Now, obviously, I don't need to give a review summary of 4.23567 star, right? I just need to do 4.2 star. Now, the size of the double is directly proportional to the amount of decimal points amount of integers after the decimal point, or the precision, right? So it is always good to specify a precision so that you only keep the data as much as you want in the level of the precision that you want, rather than keeping it at a very high precision. So that's another way to reduce the size of the data. Now, there's another optimization that we also did, which is like an extreme optimization, if you can think about it. So we had some IDs, and these are really the image IDs that are there. So when you upload an image, there is an image ID that gets generated out of it, and the image ID is of this format. It has blob IO, which is kind of the data store in which it gets stored, and then it has 2019-10-28, which is the date on which the image was uploaded, and the random UUID attached to it for uniqueness. Right? This is how a ID is generated. Now, what we did was, initially they were all stored as strings. What we said was, okay, the UUID is going to take 36 bytes. We can't do anything over there right now. This part, which is blob IO, is basically a prefix. We said we will not keep the prefix as it is. We will see how many prefixes like this come, and we will convert them into enums. We found only one prefix in our system because there was only one system. But even if there are multiple prefixes, we said we can have enums for them. Now, this part, 2019-10-28, is actually a date. Now, how do we convert a date as an integer? One way to convert a date as an integer is choose the number of days since a particular date. So we chose 1st January 2000 because Flipkart started in 2007. So you can't have a review on Flipkart before 2007. You can choose whatever day that works for you. So days since that. So 2028-10-2019 is 7595 days since 1st January 2000, which actually only requires 2 bytes to store. Right? So instead of storing 4 plus 4 plus 10 bytes, we only store 2 bytes of data to store this. Right? Now comes the UUID. So whatever ID was there, which was 18 characters, which was blob IO, the date, plus 36 bytes of UUID, now becomes 5 bytes plus 36 bytes. Now, one thing you need to definitely remember is this is quite possible that you could make mistakes with it. So this is something that if the format of the ID is going to be slightly different, then your encoding format will change. So one thing you need to remember is you need to have enough validations and fallback. So our fallback is, if it doesn't conform to this format, just store it as a string. Don't bother. Right? So, but if you look at it, and we found like a 25% reduction in size by just doing this. And of course, we had enough metrics to see whether it doesn't conform to that format and all of that. Now, let's just recap as to what all we did with encoding. We used Avro, a binary format, which is much better than JSONs. Enums, wherever it is possible, than using strings. Integers, wherever it is possible. Decimals, whenever you're using decimals, you always use them with precisions. You optimize the IDs wherever it is possible. And of course, do it with caution. Now, this overall gave us a size reduction of about 70%. Right? And now our serialization and deserialization, we shorten it and say SERD, is also faster by about 30%, right? Because binary formats, serialization and deserialization is way faster than a JSON serialization and deserialization. Right? So we were at 100, we did data cleanup and we went to 90. And then with Avro encoding and more encoding reduction, we are now at 27% of the overall data size that we were at. Right? Now, we also found out that this optimizations that we do with encoding is not only used for whenever you're storing the data, but also when you're using it for inter-service communication, because the overall payload sizes reduces. If you remember the first slide, we talked about 1.5 Gbps. If we were actually sending them via Avro, we could have probably saved 70% of the overall bandwidth that is going through the network. Now, the third strategy is something that is the most common strategy that people think to when you come to reduction of data footprint size, right? Which is compression, right? And you need to remember one thing. So let's take this example. You can go type it in your terminal today. gzip is a very common compression algorithm that we use. So you just say echo hello world and you do a gzip compression and see the size. Hello world is 11 characters or 12 characters long. When it gets compressed, it becomes 32 characters long or 32 bytes long. This is kind of counterintuitive, right? How can you compress and it results in a size which is bigger than the original size itself, right? That is the reason is because there are different types of compression algorithms. There are compression algorithms which are called entropy-based compression algorithms, which kind of keep track of common patterns, and they create like a dictionary of those patterns at the start of the compression buffer, and then they use the dictionary to compress the data. So if the strings are not long enough, or if they don't have enough common patterns, these compression algorithms actually don't work. That is the problem with gzip that you see over here. There are other compression algorithms which have a language understanding. For example, like there are common words in a particular language which actually could be represented in a much shorter form, and that will give much better compression. Like the word the, is, was, they're usually used. And if you have a lot of language text and you're identifying that these can be a language understanding is available, and you rate a compression algorithm based on that, you could actually compress it much better. Now, Shoko and SMAS are two compression algorithms which work really well for language-based compressions. And gzip, snappy work for large byte arrays. Now, we wanted to use the best of both worlds. So what we did was we used a combination of both. We used Shoko for text compression, and we used Snappy for binary compression. Right? And we were able to get a combination of both of this. And the overall reduction from Shoko came to 10%, and Snappy came to 25%. This overall reduced the data size by around 35%. So right from 100, we came to 90, then we came to 27, and then we came to now 17% of the overall data size. Now let's come to UUIDs. A lot of people would have used UUIDs in their systems for generating uniqueness. But let's first understand what is there inside a UUID. People would have just looked at it as a string. Let's look at the anatomy right now. A UUID is 128 bits, which means it is 16 bytes in length. It is represented in hex. What it means is you will never see a letter apart from 0 to 9 or A to F over here if you look at it keenly. So the A over here is not the ASCII A, it's the hex A. Right? It is 32 digits with 4 hyphens with an 8, 4, 4, 12 pattern. All of us would have seen this, right? Now, most of us store the UUID as a string. So if I'm going to store 32 digits as strings and 4 hyphens, it comes to 36 bytes, which is 288 bits. Now, what you're actually doing by storing a UUID as a string is what would have taken 128 bits if you had stored it as a byte array, now takes 228 bits when you store it as a string. So just by storing the UUID as a byte array and not as a string makes it 55% smaller. Right? Now, most of us would be storing UUID as a string, and you might be wondering, how do I store binary arrays in all my data stores? Interestingly, almost all the data stores like Mongo, MySQL, Avro, etc., all of them support for UUIDs. Okay, so MySQL has it has a function, Mongo has a data type, Avro has a data type. So it supports all these functions so that you can use UUIDs better and store them better. Now, the interesting question that you ask is, okay, you had a UUID, you're storing it in a wrong way by storing it as a string maybe, but you might also want to think whether you really need a UUID. Now, if you have a database which can generate unique IDs, you really don't need a UUID. UUID is really required only when there are multiple parallel clients who are talking to you, and all those clients are generating their own IDs, and there could be a conflict in them. But using database IDs as your primary IDs as UUIDs, when you have a central DB which can generate IDs, is probably not the good idea. Now, the other problem when you use a UUID as a primary key in a database is also that they don't index so well. Typically, MySQL and all of them, they don't index so well, and they're extremely bulky. So the idea is you don't use UUIDs if you don't need them, but as client reference IDs, it kind of makes sense. Now, in our use case, our review ID was a UUID. What it meant is every review that was given was a UUID, which was the primary key. Now, a customer writes a review for a product, and what we'll need to keep as an index is for a product, what are all the list of reviews which are available, which is a reverse index or an inverted index, right? Now, when we did it, we identified that we were storing all the reviews in a MySQL DB. So rather than having a UUID as the primary index, we could just generate a unique number within the scope of a product as a unique ID for a review. So for a product, let's say there are two products, PX and PY. PX is in blue and PY is in green. There are reviews R1, R3, and R4. Rather than storing the IDs as R1, R3, and R4, we only create unique numbers like 1, 2, 3 for the list of IDs that is there for PX, and 1 and 2 for the list of IDs. And a combination of PX, 1 or PX, 2 is unique enough in the entire space. So if you look at the inverted index as an array, before PX used to have these 3 UUIDs, and then PY used to have these 3 UUIDs. So the index used to be this big. Right now, the index is just an array of integers, right? And it's much smaller also. Right? Now, when you think about storing them, these integers in variable length encoding, they require even more lesser space. So using UUIDs as integers gave us 75 using integers instead of UUIDs gave us more than a 75% reduction in the index size. They were also indexing the storage much faster. Along with it, when we are storing integer arrays, we used a compression algorithm called fast P4. Now, fast P4 is very suited for compressing integers arrays and taking much lesser space to store them. I'll urge you to go read about it. And that gave us a further improvement, and it reduced the overall data size by 94%. Right? So what was 100% of the original index size now only takes 6% of the original index size. So overall, wrapping it up, what we saw is we saw more than a 90% reduction in the overall size. And because we were able to get to a 90% reduction in the overall size, we could actually cache a lot of this data on the app itself. Now, what does that mean? So our data size from 4.2 TB reduced to almost 150 GB. We had more than 100 instances which were storing this data. Now we have it only in 6 instances. Now, because we were able to cache the data a lot in memory on the app, our latencies dropped, and it dropped tremendously from 400 milliseconds on the P99 to 10 milliseconds on the P99. And this also gave us a 5x improvement in the overall node throughput, which meant that what a node could support, because it was doing all the network calls and the serialization and deserialization, all of that is gone because a lot of data is cached in memory. The per node throughput increased by almost 5x. Okay, so let's just recap. We saw a lot of things. Let's just do a quick recap. No JSONs, use binary. Whenever you're storing data, passing data, think about using a binary format. Binary is always smaller, faster, and cheaper. Use enums than strings wherever possible, and use integers wherever possible. Look for your data in which you can represent them as integers. Whenever you're using a double, always use it with precision, and understand the compression algorithm that you are using whenever you're trying to compress it. A wrong compression algorithm might bloat up your whole data size. Now, look for unused data or duplicate data and do a constant cleanup. Relook, optimize, and repeat is what is going to reduce your data size. Now, when you look at all of this, we can actually take a leap forward, and we can think about making our application scale to much bigger sizes by taking a less data footprint over here. I've added a list of references. You can take a look at them when you about this talk. And there's also a tech blog that is written about this in a lot of detail. I would encourage you to go read about it. Go to any questions. Okay, we have a question on Avro versioning evolution. How to keep it in the repo. Okay. How does data migration work when you store schema and data separately, although there will be multiple network calls for schema and data anyway? Oh, okay. So the schema is usually something that does not have a lot. We don't have a lot of schemas. If you think about an overall evolution of a product, right, the review schema would change by probably 10 times or 20 times in the entire life cycle of 10 years, maybe 100 times. Right. So the schema is actually kept in memory, because schema is just a particular set of string encoded in a particular value, which says this is a schema. So Avro schema is actually kept in the memory of the object, and it takes few KBs of size. So we don't actually look up the schema anywhere. We only look up the data. Now the data's first byte, because we can store up to 128 schemas. There are different ways of doing schema versioning, but the choice that we have done is the first byte of the data is basically a reference to the schema identifier. And now we can have 128 schemas, 160 schema versions. So what we have used is we've encoded the schema version in the first byte, and then we use that to identify it from the code. And that's how schema versioning kind of works. And there's no network calls that is being done. Cool. I think we are out of time. And we will be at the networking launch, and we will take all these questions in the networking launch. So people who have these questions over here, please feel free to come to the networking launch. We'll take it up there. Thanks a lot. Yeah.
Thank you so much, Anantharam, for such a wonderful session. All of you folks who are here, you can continue the Q&A in the networking launch. Anantharam will meet you there. In case you have any other further questions, do go over and clarify them with him. You can also rate this session with the poll that is launched on the right side of your screen. Do tell us how you liked Anantharam's session, and we'll definitely convey it to him.